morning friends. Already we discussed about the intrinsic conductor, that means the pure semiconductor. Right? The pairwise semiconductors are silicon and germanium. In pure semiconductor, at 0 Kelvin temperature, that means at absolute temperature, all the valence electrons are bound in covalent bond, because the silicon and germanium possesses the 4 valence electron. But at 0 Kelvin temperature, this valence electron forms the 4 covalent bond with its neighboring 4 other silicon or the germanium atom. Therefore, at 0 Kelvin temperature, there are no valence electron in silicon or the germanium crystal. Therefore, at 0 Kelvin temperature, silicon and germanium behave as the perfect insulator. Right? As the temperature increases, so some covalent bonds are broken. Electron becomes the prey from the covalent bond and take the part for the conduction of electricity. Therefore, the conductivity of semiconductor increases with time. Right? Okay. Now today we are going to discuss about the extrinsic semiconductor, or in other words, why the impurities are added in pure semiconductor. Mention the condition of impurity atoms and also explain the impure semiconductor, how we can obtain the extrinsic semiconductor. Okay. For that purpose, what is the importance of the impurity, or why the impurity are added in pure semiconductor? We know that, just we discussed, in pure semiconductor, as the temperature increases, covalent bonds are broken, so as a result, the some electron becomes the prey which take the part for the conduction of electric charge. Therefore, the conductivity of intrinsic semiconductor depends on its temperature. And at the room temperature, the conductivity of pure semiconductor is less. To obtain the more conductivity, it is necessary to add the impurity in pure semiconductor. Right? Therefore, the conductivity of intrinsic semiconductor depends on its temperature. Right? At room temperature, its conductivity is less. Therefore, to increase the conductivity, the impurity are added in pure semiconductor. Clear this thing? So there is the importance of the adding of impurity in pure semiconductor to get the drastic change in conductivity of the pure semiconductor. It is necessary to add the impurity. When a small amount of suitable impurity, how much small amount? That means the ppm, parts per million, very small parts, respect to the million atoms are added to pure semiconductor, the conductivity of semiconductor increased manifold. As we add the small part of the impurity atom or the other element, so what's happened? The very large increase takes place in the conductivity of semiconductor. And such material are known as extrinsic semiconductor. After adding the impurity in pure semiconductor, the semiconductor is known as extrinsic semiconductor. Again, when a small part or the small amount, ppm, that means the parts per million of suitable impurity is added to pure semiconductor, the conductivity of semiconductor increased manifold. Such material are known as extrinsic semiconductor. Now, the process of adding a desirable impurity is known as doping. The process of adding a desirable impurity is known as the doping. As we add the impurity in pure semiconductor, the adding process is known as the doping. Again, the definition of doping. The process of adding a desirable impurity is known as doping. And the impurity atoms are known as the dopants. What are the elements or what are the atoms are added as impurity? This atom is known as the dopants. And after adding the impurity, whatever the material is obtained is known as the doped semiconductor. That is known as doped semiconductor. The material is also known as the doped semiconductor. Again, what is the doping? The process of adding a desirable impurity is known as doping. Now, what is the dopants? The impurity atoms are added is dopants, and whatever the new material is formed, that is known as the doped semiconductor, or the extrinsic semiconductor, or the impure semiconductor. Okay. Now, what are the conditions, or which type of the dopants are added, or the impurity atoms are added? First thing, the condition is that the dopant to be such that it does not distort the original pure semiconductor lattice. So after adding the impurity atom in pure semiconductor, the lattice structure of the pure semiconductor does not change. Therefore, the dopant to be such that it does not distort the original pure semiconductor lattice. It occupies only the original semiconductor atom site in the crystal. So whatever the atoms are added, they only occupy the space at original semiconductor atom in a crystal. Now the next necessary condition is that the size of the dopant and the semiconductor atom should be nearly same. No anyone or any atoms are added as an impurity atom. But what are the dopants are added? The size of the dopant and semiconductor atoms must be equal or the same. And as a result, the lattice structure of the pure semiconductor is not distorted. Right? So there is the two conditions to select the atoms as an impurity. Right? Again, the dopant to be such that it does not distort the original pure semiconductor lattice. It occupies only the original semiconductor atom sites in crystal. And the necessary condition is that the size of dopant and semiconductor atoms should be nearly equal. Therefore, the silicon and germanium are tetravalent and they belongs to fourth group in periodic table. Silicon and germanium are tetravalent and they belongs to fourth group in periodic table. And therefore, the dopant element taken from the fifth or third group. Fifth or third group. There are two types of the dopants used for doping in silicon or germanium, whose valency is 3 or 5. So here we can select the dopant element or the dopant atom from either third or the fourth group of periodic table, right? Whose valency is either 3 or 5. Now, pentavalent impurity atoms, or the pentavalent. The arsenic S, antimony Sp, and phosphorus P are the pentavalent impurity atom. This type of the impurity are also known as the donor impurity. Arsenic, antimony, and phosphorus has the 5 valence electron, right? Therefore, these three elements are known as, or these three dopants are known as pentavalent. And this type of the impurity are also known as donor impurity. Now the next is the trivalent. Aluminium, indium, iron and boron B are the trivalent impurity atoms. It has the valence electron are 3, or it possesses the 3 valence electron. This type of the impurity are also known as the acceptor impurity. By the doping process, or the doping process provides the two type of the semiconductor, N-type and P-type semiconductor. Clear this? Again, repeat. What is the importance of the adding the impurity atom in pure semiconductor? What are the conditions for the impurity atoms? And what is the extrinsic semiconductor? Now we know that conductivity of intrinsic semiconductor depends on its temperature. At room temperature, the conductivity is very less. To increase the conductivity, impurity atoms or the impurities are added in pure semiconductor. So main purpose of adding the impurity atoms is to increase the conductivity of a semiconductor at room temperature. When a small amount ppm, parts per million of suitable impurity is added to pure semiconductor, the conductivity of semiconductor increased manifold. Such material are known as extrinsic semiconductor. When the small part of the suitable impurities are added in pure semiconductor, the conductivity of a semiconductor increased manifold. And whatever the new semiconductor is formed after adding the impurity, that is known as the extrinsic semiconductor. Now, the process of adding a desirable impurity is known as the doping, and the impurity atoms are called dopants, and such material is known as doped semiconductor. The process of adding the desirable impurity is known as the doping. The impurity atoms which are added is known as the dopants, and whatever the new semiconductor is formed, that is known as the doped semiconductor. Here the conditions are the dopant to be such that it does not distort the original pure semiconductor lattice. That means whatever the dopant is added in pure semiconductor, it cannot distort the lattice of the pure semiconductor. It only occupies the original semiconductor atom sites in the crystal. It can only occupy the space at the position of original pure semiconductor atom. Second necessary condition is that the size of dopant and semiconductor atoms must be same. That means the size of the dopant atom and semiconductor atom must be same. Here the silicon and germanium are tetravalent and they belongs to fourth group in periodic table. And therefore, the dopant element taken from either third or the fourth group of periodic table. There are the two types of the dopants are used for doping process, whose valency is 3 or 5. First is the pentavalent impurity atoms, arsenic, antimony, and phosphorus are the pentavalent impurities. This type of the impurity are also known as the donor impurities. Next, second type is trivalent impurities. Aluminium, indium, and boron are the trivalent impurities. This type of the impurities are also known as the acceptor impurities. The doping process provides the two types of the semiconductor, N-type and P-type. Clear this? After the discussion of different type of the impurity atoms, as we add the different kinds, that means the pentavalent or the trivalent impurity atom in pure semiconductors, we obtain the N-type semiconductor and P-type semiconductor respectively. Now, we are going to discuss about the N-type semiconductor, that is the extrinsic semiconductor. Right? When the pentavalent impurity atoms, like as the arsenic, antimony or the phosphorus, are added in pure silicon or germanium semiconductor, what's happened? The pentavalent impurity atom has the 5 valence electron. Out of 5 valence electron, 4 valence electron of arsenic, antimony or phosphorus are bound in covalent bond with its 4 neighboring silicon or the germanium atom and forms the 4 covalent bond. While the 5th electron is the extra electron which is joined with arsenic, antimony or the phosphorus atom with the less energy. Right? So we are going to write the answer of this question. When pentavalent impurity like arsenic, antimony or phosphorus are added in pure silicon or germanium semiconductor, out of 5 valence electron, 4 valence electrons are used to form 4 covalent bonds with neighboring for silicon or germanium atoms. That means the 4 covalent bonds are formed with help of the 4 valence electron of the pentavalent impurity. While the 4th electron, while the 5th valence electron is an extra electron bound with impurity atom with less energy. To make this electron free, it requires 0.01 electron volt energy for silicon, sorry, for germanium, and 0.05 electron volt energy for silicon. When this 5th electron gets this energy, so at that time this electron becomes the free or the separate from the impurity atom. at room temperature, silicon and germanium semiconductor has the band gap energy 0.72 electron volt for germanium and 1.1 electron volt energy for silicon. At room temperature, 0.72 electron volt energy for germanium and 1.1 electron volt energy for silicon semiconductor already have. Thus, fifth electron is obtained as free electron. In host crystal of germanium or silicon. Germanium or silicon. Clear this? How the N-type of the semiconductor is formed when the pentavalent impurity like the arsenic, antimony or the phosphorus are added in pure silicon or germanium semiconductor. Out of 5 valence electron, 4 valence electron are used to form the 4 covalent bond with neighboring 4 silicon or germanium atom. While the 5th valence electron is an extra electron bound with impurity atom with less energy. To make this electron free, it requires 0.01 electron volt energy for germanium and 0.05 electron volt energy for silicon. At room temperature, 0.72 electron volt energy for germanium and 1.1 electron volt energy for silicon semiconductor already have. Thus, the 5th electron is obtained as a free electron in host crystal of germanium or silicon. Right? After adding the pentavalent impurity in pure semiconductor, the numbers of the free electron or the valence electron are obtained. Right? In addition of this free electron, due to the broken of covalent bond with increase in temperature, the pair of electron and hole are formed. Right? In addition, due to increase in temperature, covalent bonds are broken and electron hole pair are formed. Thus, after adding pentavalent impurity in pure semiconductor, the number of free electrons are more than numbers of holes. the electron has negative charge therefore such semiconductor is known as N-type semiconductor. N-type semiconductor. Suppose the number density of an electron is any and number density of one is NH. Therefore, for N-type semiconductor, number density of electron is much greater than the NH, number density of 1. Right? Okay, what is the structure, the lattice structure of the N-type semiconductor? These are the pure silicon or the germanium atoms. Yes, we add here the arsenic or the antimony or the phosphorus atom. That is the plus 4 valency or the valence electron, plus 4 represents the silicon or the germanium atom. So here there is the plus 5, there is the arsenic, antimony or the phosphorus. So it has the 5 valence electron. Out of the 5, the 4 are bound in covalent bond with its neighboring 4 silicon or the germanium atom. 4 covalent bonds are found by saying the 1-1 electron. While the 5th extra electron is bound with the arsenic or antimony or the phosphorus atom. So here the covalent bond already exists in pure semiconductor of the silicon or the germanium. So there is the lattice structure of the N-type semiconductor. Plus 4, 4. Silicon or germanium. Plus 5. For arsenic, antimony or phosphorus. Right? Okay. Now this impurity atom donates the electron, therefore there is known as the donor impurities. Such impurity atoms donate the electron. So it called donor impurities. That is known as donor impurity. Again, what is the N-type semiconductor? When the pentavalent impurity like arsenic, antimony or the phosphorus are added in pure silicon or germanium semiconductor. Now the impurity atom has, that is the pentavalent, it has the 5 valence electron. Out of 5 valence electron, 4 valence electron are used to form 4 covalent bonds, 1, these 2. Are used to form the 4 valence electron with its 4 neighboring silicon or the germanium atom. Out of 5 valence electron, the 4 valence electron are used to form the 4 covalent bond with neighboring 4 silicon or the germanium atoms, while the 5th valence electron is an extra electron bound with impurity atoms with less energy. To make this electron pair, it requires 0.01 electron volt energy for germanium and 0.05 electron volt energy for silicon. But at room temperature, the 0.72 electron volt energy for germanium and the 1.1 electron volt energy for silicon semiconductor already have. Thus, the 5th electron is obtained as the free electron in host crystal of germanium or the silicon. Okay. In addition, due to the increase in temperature, the several covalent bonds are broken and electron hole pair are formed. Thus, after adding the pentavalent impurity in pure semiconductor, the number of the free electrons are more than numbers of the hole. So, due to the adding of the pentavalent impurity atom, the extra electron or the free electrons are added in pure semiconductor. Therefore, the electrons are the majority charge carrier in this type of the electron, this type of the semiconductor. Right? Because the number of the free electron is more than the number of hole in this type of the semiconductor. Here, such impurity atoms donate the electron, so it is known as the donor impurity atom. Now, the electron has the negative charge, therefore, such semiconductor is known as the N-type semiconductor. Suppose the number density of an electron is Ne and number density of the hole is Nh. For N-type semiconductor, Ne is greater than Nx. And also, the majority charge carrier in N-type semiconductor majority charge carriers are electron and minority charge carriers are hole. So keep in mind that in N-type semiconductor, the conduction of the electric charge takes place due to the motion of the electron. Hole are also the charge carrier, but the number density of the hole is very less compared to the electron. Therefore, the majority charge carrier in N-type semiconductors are electron and the minority charge carriers are hole. Okay. Already we discussed about that to obtain the extrinsic semiconductor. We had to add the impurity atom. What's the proportion of impurity atom? For 10:8 atoms of pure silicon or the germanium atom, one impurity atom is added. One impurity atom is added. And also in 1 mole pure semiconductor, 10:17 atoms of impurities are added. That is only for our knowledge. Proportion per 10⁶ pure atom, silicon or germanium atoms, 1 impurity atom, and in 1 mole pure semiconductor, 1 mole pure semiconductor, 10⁻17 impurity atoms are added. There is okay. Now, as we understand about how the N-type semiconductor is constructed, the same thing for the P-type semiconductor form. In N-type semiconductor, we take the impurity atoms is pentavalent, while in P-type semiconductor, we have to take the trivalent impurity atoms. Right? So again, we repeat the N-type semiconductor. When the pentavalent impurity like arsenic, antimony, or the phosphorus are added in pure silicon or the germanium semiconductor, out of 5 valence electron, the 4 valence electrons are used to form 4 covalent bonds with neighboring 4 silicon or the germanium atom. While the 5th valence electron is an extra electron bound with impurity atom with less energy. To make this electron free, it requires 0.01 electron volt energy for germanium and 0.05 electron volt energy for silicon. Now, at room temperature, the 0.72 electron volt energy for germanium and 1.1 electron energy for silicon semiconductor already have. Thus, this extra electron is obtained as a free electron in post crystal of the germanium or the silicon. In addition, due to the increase in temperature, several covalent bonds are broken and electron hole pair are formed. Thus, after adding the pentavalent impurity in pure semiconductors, the number of the free electrons are more than the numbers of the holes. So, such impurity atom has, for the impurity atom, donate the electron. So, it is known as the donor impurity. The electron has the negative charge. Therefore, such semiconductor is known as N-type semiconductor. Suppose the number density of the electron is Ne and number density of the hole is Nh. For N-type semiconductor, Ne is greater than Hh. In N-type semiconductor, the majority charge carriers are electron and minority charge carriers are hole. What is the proportion of impurity atom? So, proportion per 10⁶ pure silicon or the germanium atoms, 1 impurity atom is added, and in 1 mole pure semiconductor, 10⁻17 impurity atoms are added. Sometimes the 1 marks question may be asked on the basis of the proportion. Right? So that is the N-type semiconductor.